First, thank you all for attending, the last session at the last day on such a beautiful day outside. I really appreciate it. And just a fair warning, I tend to go very fast with very fast animations. So if you're going to take pictures, you're going to need a really, really, really fast camera to keep up with me. Okay, so this talk, this work was done jointly with my advisor, Prasun, Dewan, at UNC, and it's about collaborative applications. So let me start by defining what we mean. Collaborative application is an application shared among users in such a manner that the input of one user affects the views of all users. So consider a shared checkers game. If one user enters a command to move a piece, the piece moves not only on that user's machine, but also on the machine belonging to all of the other users. Applications is extremely important. And I'm going to illustrate that with a little story, but I need to provide a little bit of context so the story makes sense. So some of you may know, college sports and especially college basketball are really, really big in the US, and they form really strong rivalries between schools. And none of those is stronger than the rivalry between my school, North Carolina, and Duke University. Okay, so keep that in mind as I give this little story. Each year, the computer science department at UNC holds a candidates day where they invite a number of potential graduate students to come see demos of the kind of work done in the department. Unfortunately, some of these students are also invited to the Candidates Day at Duke, which takes place on the same day. So to give all of the invited students a taste of research at UNC professors shared a demo application using an application sharing system. Now, the performance of this system is very important because if it provides poor interactivity to the student at Duke, the student may get bored and as a result quit the session. Therefore, the student may not end up coming to UNC. What's much worse, the student may end up going to Duke. There are many performance metrics for collaborative applications. There's response times, jitter, throughput, task completion time, bandwidth. While all of them are important, our focus was on the response times. Response time is defined as the amount of time that elapses from the moment a user enters a command to the moment that user sees the output for the command. The is defined as the amount of time that elapses from the moment some user enters a command to the moment another user sees the output for the command. Response times in many ways. I could increase processing powers, I could reduce latencies, I can improve bandwidth, I can optimize collaboration architectures, I could deploy multicast, but I'm not going to do any of that. Instead, I'm going to look at to try to improve performance with scheduling. Okay? I need to define the tasks that I'm going to schedule. So let's derive these tasks from our little scenario in which users are playing checkers. So the fact that a move appears on all of the user's machines when a user makes it means there's some processing going on. And the fact that a move moves from the inputter's machine to all of the other users means that there's some sort of transmission going on. Now, there could be other tasks belonging to concurrency control, consistency maintenance, awareness mechanisms, and also local-only user commands. And while all of them are important in general, only the processing and transmission of user commands is mandatory, and those are the ones we focused on. Let's see, so we know the tasks we want to schedule. Let's see what units we have to schedule them on. Obviously, we have the CPU, which can be single core or multi-core. But these are not the only processing units in a computer. There's a processor on the network card, which can perform some of the transmission tasks. There's also a processor on the graphics card, which can perform some of the processing tasks. In this talk, we're going to focus on scheduling the mandatory tasks on the CPU and the network card processor. Now scheduling, carrying out the processing task is pretty straightforward. The CPU simply has to execute it. But let's look at a transmission more complicated. For a command to be transmitted, the CPU must first copy the command data to some location in memory from which the network card will then read that data and eventually transmit it on the physical network. So there are really two transmission tasks, the CPU transmission task and the network card transmission task. The CPU transmission task is schedulable with respect to CPU processing, while the network card transmission task is not. It simply follows CPU transmission. Now, if we use non-blocking communication, then this network card transmission task can in fact run parallel with the CPU processing, and the rest of this talk we assume non-blocking communication. So overall, we say that the CPU transmission task is schedulable, while the network card transmission task is not. So if we have a multi-core system, let's see which ways we can schedule these tasks. Okay, we can use a parallel policy in which the processing and transmission are done on different cores using one core for each. Okay. Well, could we parallelize the processing task? In general, the processing task is defined by the application. It's sort of a black box. So it's not really possible to parallelize it explicitly by any external framework. So we don't consider schemes in which the processing task is parallelized. What about the transmission task? I mean, if you're transmitting to multiple destinations, you can have multiple cores transmitting in parallel, and this should help. Well, not really, because a single core is enough to saturate the network card. So using more than one core is not going to help for remote response times. And in fact, by using multiple cores to transmit, it makes it difficult to predict remote response times. The reason is when multiple cores make a send call, the operating system can schedule those in an arbitrary order, which means we don't know the order in which the network card is going to transmit in, which gives us problems with predicting remote response times. Okay, well, what about scheduling these on single core machines? Okay, so we have two tasks, processing and transmission. We could process first, transmit second. Or we could transmit first, process second. Or we could schedule them concurrently. So we have options here, and if one of these policies dominates all of the others, then we don't really have options. We use the one that dominates. So let's see whether one does dominate any of these other ones. Well, the process first policy is going to give you good local response times because you process first and then transmit, but because of that, it gives you poor remote response times. Now, the transmit first policy, on the other hand, gives you good remote response times because you transmit first, then process, but it gives you poor local response times. And the concurrent policy, we can expect it to give you kind of response times in between those provided by the other two policies. Now, one issue, so none of them really dominate each other, but one issue here is that we can't really control the trade-off between local and remote response times easily. It's kind of an all or nothing thing or something murky in between that we don't know. If we could, for example, control this trade-off, so for instance, what if we could what if we could let the local response times increase unnoticeably, but trade that off for noticeable decreases in the remote response times? In this case, the local user stays happy because they cannot notice the increase, but the remote users become happier because suddenly their response times improved. Okay? You can imagine dual of this policy where we reverse the trade-off, but in today's talk we focus on the first one. Previous research has shown that there are indeed some response times differences that are noticeable. So first of all, local or remote response times below 50 milliseconds are not really distinguishable to users, but increments and decrements of 50 milliseconds for both local and remote response times are noticeable. So we created a policy that uses these psychology results to schedule a task in a slightly different manner. The idea behind this policy is to temporarily delay processing. And while the processing is delayed, the CPU transmits to as many destinations as it can, but only while the delay is below noticeable. As soon as another transmission would make the delay noticeable, the CPU stops transmitting and performs the processing task. And only when the processing task completes, the CPU completes the rest of the transmission. Okay? Now, one interesting side effect of this policy is that it reduces differences between local and remote response times. And we've seen this kind of same goal in what's called local lag, done by Struckle and Goodwin. And there's some interesting comparisons between lazy policy and the local lag approach. So for instance, the lazy policy never lets it uses local lag, but it always keeps local lag below noticeable. Okay? And secondly, it tries to kind of perform some useful things during the lag. So for example, it tries to transmit to as many destinations as possible. And you can also imagine that instead of transmitting, it could say, well, while I'm delaying local processing, I'm going to process as many commands coming in from the remote users. Okay? And this leads nicely to comparison with timelines, which we saw earlier in this conference by Cheryl Savory and Nick Graham. And the goal there is they say, look, there's going to be some time between commands going between computers. So whenever you execute a command locally, if you're executing against some remote state, your remote state that's local is out of sync, and what you need to do is somehow predict what the correct local state is, remote state is, and execute against that. Well, if you lazily delay execution of the local command that requires extrapolation of a future state, then the chances improve that the commands that would update the remote state for you locally are going to arrive, and therefore it's going to reduce, execution against incorrectly predicted future state, and the net result is that the jarring effects in the user interface that occur would be reduced. Okay, so now let's intuitively think which policies are dominant. Well, we saw that the lazy policy gives us improvements in response times of some users without noticeably degrading the performance of others. So compared to the process first policy, the local response times are not noticeably different, and this is by design. Okay? But the remote response times are noticeably better than those of process first. Okay? So by the way, what I've just proven here is that in computer science, there is such a thing as free lunch, because we were able to get something for nothing. The lazy policy dominates process first. And since it kind of replaced the process first policy, which was neither not dominant nor dominated by concurrent or transmit first, we can intuitively say that none of the lazy, transmit first, and concurrent policies dominate each other. With multi-core, we only have one policy, so we know it's the dominant one. And multi-core parallel policy dominates all single core policies. Or does it? Let's take a closer look at this one. This is a theoretical example, carefully constructed to show interesting results. Consider 10 users, where one user is entering all of the commands, user 1. And they're organized in some sort of multicast communication tree where user 1 sends commands to user 2, 3, 4, 5, and 6, and user 2 forwards commands to user 7, 8, 9, and 10. And let's say that and all the computers are multi-core. Now let's say that the CPU transmission time is 10 milliseconds for all users, for all computers. Network card transmission time is 30 milliseconds. Processing time is 40. Network latencies between all computers are 20. And of course, the noticeable threshold that's required by lazy is 50 milliseconds, as shown by previous work. Let's analyze user 10's remote response times for commands entered by user 1. And let's first do the parallel policy. And without loss of generality, let's say that core 1 is doing processing and core 2 is doing transmission. So when user 1 enters a command, user 1's computer is going to process the command in core 1. Meanwhile, core 2 is going to say, okay, I'm going to transmit to user 2. And as soon as the CPU transmits to user 2, the network card is going to pick up the transmission. As soon as it's done transmitting, the command is going to traverse the network to reach user 2's computer. And when it does, user 2's core 2 is going to say, okay, I'm going to send this command to user 7, 8, 9, and 10. And as soon as the CPU and user 2's computer sends it to user 7, the network card kicks in, and it's a little bit slower, so it takes a while to actually transmit a command to user 10. When it does, the command traverses the network to reach user 10's computer, and finally, the user 10's computer processes it when the command reaches it. So we get a response time of about 220 milliseconds. Now let's see if we use the lazy policy. And even though these are multi-core machines, let's just suppose that we're using only one core in all of the machines to schedule all of these tasks. So when user 1's computer receives a command, it's going to say, can I delay processing of this command without my local user noticing? Well, transmission time is, CPU transmission time is 5, noticeable delay is 50, 5 is less than 50, definitely I can transmit to user 2. As soon as it transmits to user 2, the network card then transmits to user 2, picks up the task. When it does, the command traverses the network to reach user 2's computer. Now when user 2's computer receives the command, it says, can I delay processing without my local user noticing? And what it does is it says, what is the total delay so far in all of the machines before the message got to me? And there was only one machine, user 1, and the total delay was the CPU transmission time plus the network card transmission time, which is 35 milliseconds. Okay? That means the user 2's computer has about 15 milliseconds left to delay the processing task without the local user noticing. In 15 milliseconds, that computer can transmit to 3 destinations, user 7, 8, and 9. Okay? And then it's going to stop transmitting, carry out the processing task, and only once the processing task finishes, it's going to transmit to the 4th user. Now, when it transmitted to user 7, of course, the network card started transmitting to user 7, and since it's going slow, it takes some time. In fact, it's going slow enough in this example that by the time the CPU transmits to user 10, the network card is still busy transmitting to user 8. Okay? So it's going to take some time before it gets to transmitting to user 10, and when it does, the command has to traverse the network, reach user 10's computer, which is going to process it, and we get the response time that's the same as that of the parallel policy. So what this example shows is that in this case, the single core lazy policy is as good as multi-core parallel. And I can go for the rest of the users too if I just pick one. Okay, overall though, the multi-core parallel policy does dominate single core policies, but it's not necessarily better. Okay, so lazy single core policies can give you just as good a performance, and that's kind of interesting because now you can say, even though I have multiple cores, I'll just use one for the collaboration tasks, and I'll use the other core for whatever else I want to have. Yes, have a choice of these various scheduling policies. An interesting question, or at least to me, is can we automatically select the optimal policy? Okay, to do that, we're going to need some sort of analytical model that's going to predict response times for all of these scheduling policies. And we have one, it's presented in the paper, and I'm not going to go into the details here. Of course, we would need a system that can gather the values of all of the parameters in the model so that it can apply the model online and actually pick the policy that works. And this system, we have implemented it. It's got many complex implementation issues beyond the scope of this paper. And details are in my dissertation, and we have another paper in progress for that. But for now, I'm not going to talk about it. But you know, it is very complex. So the actual question is, okay, I have this complex system. Are there really any practical benefits to it in real world? Well, in order to do that, we can maybe simulate performance using our analytical model. And if we want, you know, practical scenarios, we need practical simulations. Okay? A distributed PowerPoint presentation. So if we need first thing we need is realistic values of PowerPoint transmission and processing times. We gather them, we measure them from actual logs of PowerPoint presentations, and in this case, I'm doing a single core simulation scenario for now, and we measure them with 3 different single core machines: a netbook, a P4 desktop, P3 desktop, where the P3 desktop is sort of meant to simulate the power of next generation mobile devices. And let's suppose that the presenter is using a netbook to give this. There are 600 other people observing it. It's a big talk. And they're using a variety of single-core devices for this. Suppose that out of these 600 users, 6 are the forwarders. So 6 users are forwarding to 99 other users, okay, in a manner like this. And latencies between the forwarders are low. That is, those guys are close together. But the rest of the users are spread around the world. So we need realistic latencies to them, and we got them by using substantive latencies measured between actual computers around the planet by previous work. Here are the results. So the local response time results show us that the lazy local response time is noticeably better than that of transmit first. And while in this scenario, it wasn't noticeably better than concurrent, it can be in other scenarios. Now here are the remote response time results, and to read this table, you kind of read it like this. It says the number of users whose lazy remote response times are equal to, noticeably better, noticeably worse, not noticeably different than those of transmit first is, 407 is equal to transmit first. The majority get equal response times with lazy and transmit first. For 5 users, lazy is better. And for 187 users, lazy is not better. And in this particular simulations, the numbers would happen to be the same for the concurrent policy. Now, if we kind of look at the interesting groups of results here, we say, look, none of the transmit first, concurrent, and lazy policies dominate each other. Okay? You can always find some users that are going to get better response times with any one. But let's look at more closely at the 5 users who have better response times with lazy than with the other ones. It turns out that 4 of these 5 users are the forwarders. They're the guys doing all the work. Okay? So in some sense, the lazy policy is more fair. They're transmit first and concurrent. What we see here is that each policy can be significantly better than other policies for some users. So how are we going to actually pick the policy that's the best? We could take a simple approach and say average response times and say that whatever policy gives the best average response times, that's the one we're going to pick. So let's walk through a quick example for that. Let's go back to our professor and student scenario. And suppose that one policy, that we have 2 policies, both of which give 100 millisecond response times to the professor. One gives 100 millisecond response times to student 1, the other one, and 200 milliseconds to the other, while the second policy does the opposite. So if we look at the average response times, then obviously the 2 scheduling policies are the same. Some response times some users are more important than others, so response times to them are more important. For instance, what if student 2 has financial aid and student 1 doesn't? We really want to get that student with financial aid. Yeah. In this case, we can see that actually the 2 policies are not the same because policy B gives better remote response times to the student with financial aid than policy A. Now, to make we needed external criteria from the users. And in this case, the criteria was favor the important users, and the data needed for that is the identity of the users. It could have also been favor local or remote response times, and the data needed to enforce that would be the identity of users who input and those who observe. In general, the criteria are arbitrary and can require arbitrary data to be enforced. So users are the ones who must provide response time functions that encapsulate their criteria. And we can then, if they provide us such a function, watch what can. All right. If the users want to improve as many response times as possible, then in our simulation, we use concurrent or transit first. If, on the other hand, users want to improve as many remote response times without noticeably degrading local response times, then we should use the lazy policy. And if the goal is to improve as many remote response times as possible without noticeably degrading local response times and the remote response times of the forwarders, the guys doing all the work, then again, use the lazy policy. And in this case, we assume that we know the forwarders ahead of time. Single core simulations results. Let's take a quick look at a multi-core simulation scenario. And it's very similar to the one we just saw. It said this time everybody's using multi-core machines. And instead of 1,200 users, and the 6 forwarders are transmitting to 199 users each instead of 99. Okay. Follows. The parallel local response time is noticeably better than the transmit first local response time, but not noticeably better than lazy. Okay. And the remote response time results show that the parallel policy gives noticeably better response times to 5 users, but for everybody else it's not noticeably different. And more interestingly, compared to the lazy policy, for all but one remote user, lazy and parallel give exactly the same remote response times. And for the one user that they're different, they're not noticeably different. Okay, so this kind of confirms our theoretical result that we saw, that the single core lazy policy can be as good as multi-core parallel. Okay. So if we have a user response time function in this case that says improve as many response times as possible, then might as well pick the single core lazy policy since we're saving all the remaining cores for other tasks. But there are cases when the parallel policy is going to be better, and since there's only one multi-core policy, we would just pick the parallel one. Okay. Now, all these policies and the model and enforcing it is sort of complex. So, would you recommend this approach to software designers? And the real question is the added complexity worth it? Well, yes. If performance of current systems is an issue, and it can be improved, okay? So when can it be improved? General is a function of resources, okay? And when resources are insufficient, performance is always going to be bad. There's nothing we can do. When resources are abundant, performance is always good, we're happy. These two cases bracket the case called the window of opportunity, in which resources are sufficient but scarce, and it's possible to improve performance from poor to good. Okay? So we're living kind of in this world, and we believe it exists now, it exists in the future. I'm almost there. So for instance, in the future, every device is going to have more and more cores. And as you get more and more cores, of course, just use the parallel policy. And therefore, the choice of policies is not important. Well, with more and more cores, the energy costs go up, which is one of the reasons we still see most, if not all, cell phones, PDAs, and netbooks still using single-core CPUs. And so the choice of scheduling policy is going to stay important at least for a while. So we've studied scheduling on variable cores, including multi-core CPUs and the processor on the network card. We defined a parallel scheduling policy. We have an analytical model for variable core scheduling policies. And we showed simulations that show that there are practical benefits to choosing the right policy in practical scenarios. And we defined a user response time function that can be used to actually select the policy that's going to best meet users' response time requirements. Picture. We would like to create a self-optimizing scheduler that automatically selects a policy that best meets response time requirements. And not only the scheduler, we want to make the schedule part of a global optimizer that's not only going to optimize scheduling, but also the processing and the communication architecture. And of course, we want to expand our analytical model and therefore our system to handle applications that have those optional commands such as concurrency control, consistency maintenance, awareness, and so on.